Well, good morning, everybody. This is a tutorial on tropical algebra and geometry for machine learning optimization. I'm sorry for the late start. There was a rescheduling of my flight. So let us begin. Well, tropical algebra and geometry are essentially new fields in mathematics and computer science. And especially tropical geometry has recently emerged as successful methodology for analysis, design, and understanding of several classes of problems and systems in both classical machine learning Yes, I was saying that tropical geometry has recently emerged successfully as a methodology for analysis, design, and understanding of several classes of classical machine learning systems, as well as deep learning systems like deep neural networks. And in this tutorial, we will first summarize some introductory ideas and tools from tropical geometry and its underlying max plus algebra, which I call tropical algebra, for reasons that will be understood later on during the tutorial. And then we will focus on how this new set of tools can aid in the analysis design of several classes of neural networks. Let us first give a meaning to the word tropical. Well, this adjective was coined by French mathematicians who were trying to honor their Brazilian colleague, Imre Simon, who was a pioneer of mean plus algebra as applied to finite automata in computer science. This adjective was suggested by these French mathematicians in a playful way. But in this tutorial and in these works that you will see the word tropical, we give it a more substantial meaning from the Greek word tropi, which means turning or changing the way or direction. And here you see a tropical line, which is actually a polygonal line that turns around corner points and forms a polygonal path. So in this tutorial, after the introduction of some key ideas and definitions from tropical geometry and max plus algebra, I will show how these tools can be applied to neural networks, both shallow and deep, which contain piecewise linear activations. Then another class of neural networks that is similar to them, that contains nonlinear nodes of the max plus type. Then we will discuss how these ideas can be also applied to optimization problems. And then we will, the last section will be about nonlinear regression, piecewise linear regression. Here are the names and photos of my collaborators in the works that I will be summarizing in this tutorial. So let me start from tropical geometry, which according to one of the few books in the area by McLagan and Sternfels, they essentially refer to it as a marriage between algebraic geometry and polyhedral geometry, or a piecewise linear version of algebraic geometry. From our viewpoint, tropical geometry is a so-called dequantized version of Euclidean geometry, and I will explain later what is the meaning of this process called dequantization. There are not that many books in the area yet. One of the few books is the one I mentioned by McLegan and Sternfels. Another book on tropical algebraic geometry is by, actually it's a collection of papers by Ittenberg, Mikalkin and Sustin. Then some tropical combinatorics, which is more tropical algebraic viewpoint by Joswick. And then there are several key papers by the French Max Plus group, Stéphane Goubert, Marianne Akian, and their collaborators, as well as the books by Cunningham and Green and Butkovich that talk about minimax algebra, another word of Max Plus algebra, and some key papers by a Russian team, Maslov, Litvinov, and their collaborators, who have founded an area in mathematics called idempotent mathematics. And in terms of machine learning, since I would say, with the exception of a paper by Pachter and Sternfels in 2004, which dealt with the first application of tropical geometry to statistical models of the hidden Markov type. So with the exception of that, the papers using tropical geometry and machine learning started appearing during the last 7 or 8 years. And here is a list of some of the key papers there. And I will be mentioning some ideas and results from these papers during this tutorial. Well, talking about tropical arithmetic replaces the standard arithmetic where we use additions and multiplications of integer or real numbers. It replaces the additions with the maximum operation and the multiplication with the addition. So one of the most well-known tropical semi-ring for scalar arithmetic is the max plus semi-ring. A dual semi-ring is the min plus, where the generalized addition is the minimum operation. So we have min plus instead of sum of products. Now, in green, you see some well-known Euclidean curves, which are the graphs of traditional polynomials using sum of product arithmetic of degree 1, 2, parabola, and the cubic 3. In blue, you see the corresponding tropical one-dimensional polynomials, which result from these Euclidean polynomials by simply replacing addition with maximum and multiplication with addition of constants. And you see that these tropical polynomials are essentially piecewise linear curves bending around several corner points. And the number of corner points depends on the degree of this tropical polynomial. Now, I have been talking mainly about max plus polynomials, max plus algebra, max plus arithmetic for the tropical geometry, but a dual view is to talk about the min plus algebra, the min plus polynomials. The max plus polynomials in blue are all convex, whereas the min plus are all concave in red. So these are the only two differences. Now, another object of interest in tropical geometry is the so-called tropical curve of a tropical polynomial P. Well, in traditional polynomials, when I say traditional, I mean using the sum of product arithmetic. We, especially for two-dimensional polynomials, we're interested in finding the zero locus of these polynomials. Well, now, the zero locus for the tropical polynomials is defined as a set of points where the maximum or the minimum is attained by more than one of the monomial terms of the polynomial. So you see in this example of this slide you see the tropical curve of a two-dimensional polynomial, p of xy, which is equal to the maximum of three terms, 2x, y, and c. C is a constant. And you see that the tropical curve is this black curve consisting of one vertex and three rays. To the right of this, you see the tropical curve of the dual polynomial, where the maximum is replaced by minimum. And you see that it also consists, the tropical curve of this p prime polynomial. With prime, we usually denote the dual functions, the dual polynomials. You see that the directions of the three rays in the tropical curve of the dual polynomial are essentially reverse directions of the corresponding ones in the tropical curve of the max plus. So remember this, max plus polynomials, tropical curves. Let's go to another geometrical object of tropical geometry, the so-called Newton polytope. Well, given a tropical polynomial, let's say in 2 dimensions, then the Newton polytope is defined as the convex hull of its coefficient vectors. So, in this example, we have a 2-dimensional polynomial with a maximum of 1, 2, 3, 4, 5 terms. We take the coefficients of every term as a vector. You will see this 5 points, and we take the convex hull of this set of 5 points. So this blue area is the Newton polytope, which of course is a convex set. Now there's a duality between the Newton polytope and the tropical curve of a max plus polynomial. So there's a duality between the two of them. We will not, mention more about this duality, and we will focus mainly on the Newton polytope. Now, so far I have been showing examples of 1-dimensional and 2-dimensional first-degree tropical polynomials. Here is a first example of a second order 2-dimensional tropical polynomial, which results in the following way. We take, for example, a Euclidean polynomial in 2 variables of degree 2, which of course has a conic surface, and then we replace all the addition of the monomial terms with minimum, and all the multiplications, we convert them into, using a logarithmic procedure that I will explain within a few slides from now. We convert them into the multiplication of the variables with some coefficients that result from the power. We take down the power with a logarithm, and then the multiplicative coefficient becomes a constant. So you see now the surface of this tropical polynomial, which looks like a tent in three dimensions. And on the plane, if you project let's say, the lines at which 2 adjacent linear surfaces are adjacent, then if you project them on the plane, you get a tropical curve of this tropical polynomial. Now, I have been talking about this process called dequantization, and I have shown in a kind of a heuristic way how to go from a Euclidean polynomial to a tropical polynomial. Or here is the formal way. The formal way is called dequantization. It comes from Maslov and his group of idempotent mathematics. It's fairly simple. Actually, in convex analysis, a simpler version of this process is known as the log-sum exponentiation approximation. The goal here is to approximate the maximum of two numbers, A and B, to approximate them with the following function and limit. We take the two numbers, we scale them with a temperature-like parameter, capital T. We exponentiate them, add them, we take the log of the sum, and then we multiply that with a scale parameter, and we take the limit of this expression when the scale parameter, or the temperature, symbolically, tends to 0. The result is the maximum of two numbers. If, when we exponentiate them, if we add a negative sign to them, then we take the minimum. We find the minimum. So then it's fairly then simple to mathematically express either the max or the mean with a limit of this log sum exponentiation expression. And if we stop before the limit is attained, then we get an approximate version. And you see on this slide, you see such an experiment. In blue, you see the graph of a tropical polynomial f of x, which is a maximum of three functions, three linear functions, f1, f2, and f3. Then in red, green, and gray, you see these approximations of this piecewise linear curve with smooth curves that are differentiable everywhere because of the exponential functions. According to where we stop the scale parameter, the approximation becomes closer or further away from the piecewise linear curve. So this is the dequantization I have been talking about. And based on this dequantization now, we can obtain tropical polynomials from classical polynomials. The classical polynomials that we're considering, they have a few constraints. The multiplicative coefficients ck of all the terms have to be positive. So this type of polynomials are called posinomials. Further, although in the literature, let's say in most of the tropical geometry literature and antipodal mathematics, the exponents of the variables u1, u2, un are considered to be integer, there is no real need to constrain this. So in our work, we leave these exponents, a1, a2, and so on, we leave them free to be real numbers. So now, another constraint is that these variables u1, u2, and so on, they are constrained to be in a quadrant of the space where all the individual components of the free variables are positive. All of these constraints because we want to take the logarithms. So taking the logarithm of the vector u gives us the vector x. Taking the logarithm of the multiplicative constant ck gives us the bias constants bk. And then by taking the log of every monomial, essentially we take down the exponents, ak, and we make them essentially slope parameters. So the result, when we take the limit for the dequantization process, is to convert a classical polynomial, to convert it into a max plus polynomial, or let's call it simply tropical polynomial. Whereas where with the word tropical, we understand both the max plus case and the min plus. But because they are dual, to simplify our discussion today, I will mainly show results for the max plus. Another way of naming these max plus polynomials are max affine functions. Because every term, it's an affine function. It represents either a line in 2D space or a plane in 3D space and so on. So we have a maximum of affine terms. Another object of interest, geometrical object of interest in tropical geometry is the concept of tropical half space. Perhaps you're all familiar from courses in pattern recognition and machine learning of a linear half space, which is defined based on a linear equation. Whereas, well, here we define the tropical half space as all the feature vectors x in a feature space which satisfy this inequality. This is a max plus. This inequality is inequality between two tropical polynomials, where the left side has coefficients A and the right side has coefficients B. And as you see from this one-dimensional example on the left, there is actually a region separate. There is a boundary that separates the two regions, and each one of these regions is a tropical half space, and this separating boundary is actually a tropical polynomial. Now, if we have several of those tropical polynomials, and each one of them defines, let's say, two regions, then by taking the intersection, a finite intersection of these tropical half spaces, we form the so-called polytopes. So the polytopes, or a polyhedra. The polyhedra, let's say, can be defined as intersection of tropical half spaces, and if these intersections are compact, then we call them polytopes. So from now on, the word polytope will mean for us a compact intersection of tropical half spaces. You see that in 3D, two tropical polynomials, a max plus polynomial f and a min plus polynomial g. The blue one is the separating surface of the max plus polynomial, which separates the space into two regions. The red one is the separating boundary for the min plus, which again separates the 3D space in two regions. If we take the intersection now of the corresponding tropical half spaces, then we end up in the bottom with a polytope. So these tropical polytopes consist of, I would say, hyperplanes, surfaces with hyperplanes, bending, and so on. Now, another concept related to Newton polytope is the so-called extended Newton polytope. I mentioned before that the Newton polytope is the convex hull of the coefficient vectors of a max plus polynomial. Look at this max plus polynomial here at the top of this slide. It's a maximum of affine terms where every term has a slope vector AI and a constant bias vector BI. Where if we take the convex hull of only the slope vectors, we obtain the Newton polytope. But if we augment the slope vector with the bias, essentially we increase the dimension by 1, then the convex hull of the higher dimensional vectors is called the extended Newton polytope. And this is really useful, a very useful object in our discussion, because it has been proven that a max plus polynomial with the same vertices in the upper hull of the extended Newton polytope correspond to the same function. So essentially a max plus polynomial as a function is determined only by the vertices of the upper hull of the extended Newton polytope. Some examples. On the left, a 1D example. We have a one-dimensional max plus polynomial that consists of 4 terms, 3x, 2x plus 1/2, x plus 1, and 0. So if we take the coefficients of these four terms, we get the four blue vertices. Their convex hull gives me the Newton polytope. But if I augment each one of these slopes with a corresponding bias, then I go from 1 to 2 dimensions, and I get the four green vertices whose convex hull creates the extended Newton polytope. And the upper hull is this green curve, and the vertices of the upper hull determine essentially the function corresponding to this max plus polynomial. Same idea in 2D, where you see a two-dimensional max plus polynomial on the right, with blue the Newton polytope, with green the upper hull of the extended Newton polytope. And here you see an example where we have, let's say, a max plus polynomial that in the beginning shows up as consisting of four terms, but actually one of them is below the upper hull of the extended Newton polytope. Whatever is below that is not necessary, it's not needed, it's redundant. It can actually it can be taken off the max plus expression without altering the function corresponding to the max plus polynomial. So then only the vertices of the upper hull count. Now, I'm ready now to define operations between max plus polynomials which correspond to geometric operations of the Newton polytopes. Because we have seen so far that every max plus polynomial is represented geometrically by its Newton polytope. So what happens then if we add or max two of these nonlinear tropical polynomials? What happens to their geometric objects, which are the Newton polytopes? One of the operations that happens is the so-called Minkowski addition. Minkowski addition is known in computer vision as dilation of shapes. Shapes represented by sets. So, for example, if we have two sets, here the first example shows the first set being a vertical column of 3 points, the other set being a horizontal segment of 3 points. If we take the Minkowski sum, which is essentially the set of all the sums of vector points A and B, where A belongs to the first set X and B belongs to the second set Y, then the result will be 3 by 3 square. And if we take this 3 by 3 square and we take its Minkowski sum with a 5-pixel rhombus, then we get this 21-pixel octagon. And if we take the last example in the bottom part of this slide, is the Minkowski sum of 2 line segments, each one of them with only 2 pixels, and the first being horizontal, the other one forms an angle of 60 degrees, the other one an angle of 120 degrees. The Minkowski sum gives us a 7-pixel hexagon. Okay, so having this in mind, we have this very useful result where if we are given 2 polynomials, P1 and P2, and we consider their Newton polytopes, which you see here on the left, with capital P1 is the Newton polytope of the polynomial P1, the capital P2, so on, then what is the Newton polytope of, let's say, the maximum of the 2 polynomials? Well, the result will be the union of the 2 Newton polytopes, the 2 individual Newton polytopes, but the union is not guaranteed to be convex. Therefore, after we take the union, we have to take the convex hull of the union. And the result here is this green shape, which is the Newton polytope of the polynomial that results by maxing the two individual polynomials. And on the right, in red or pink, you see the Newton polytope that results by summing the two polynomials, P1 and P2. The result geometrically will be the Minkowski addition of the two individual polynomials. This last operation will be very useful for understanding the geometry of neural nets. Because P1 and P2, for example, will represent two individual neurons. And then when we sum these two neurons, two hidden neurons, when we sum them to obtain, let's say, an output neuron, then the polytope of the output neuron will be the Minkowski sum of the polytopes of every neuron. Do we have any questions so far? Or we can take questions after I finish with this introduction. This was a brief introduction of concepts and operations for tropical geometry. Now follows introduction of similar concepts and examples of max-plus algebra, which is the kind of the underlying arithmetic of tropical geometry. There has been a lot of research in the last 30 years of systems using max-plus algebra. Here, I have used a color code to show several key references and areas of applications of max-plus algebra. In red, the applications essentially use finite dimensional versions of max-plus algebra. By this I mean essentially nonlinear operations using max-min or max-plus operations of vectors and matrices. That's why I call them finite dimensional. So application areas start from scheduling, operations research, finding shortest paths on graphs, nonlinear control. There is a large area in nonlinear control called discrete event dynamical systems. Also several optimization, nonlinear optimizations, where the algebra involved is max-plus. In speech and language processing, also probabilistic graphical models. Now in green, I saw application areas where the max-plus arithmetic or the max-plus algebra involves sometimes infinite dimensional spaces like signals, images. And one obvious such application area is computer vision, image processing and computer vision, or nonlinear signal processing, or nonlinear feature extraction. Also in mathematics and physics, we will see that this max-plus algebra is present. A few examples. Again, the correspondence between the ordinal, the conventional arithmetic, sum, product, and their correspondence with a max-plus arithmetic. This max-plus essentially ring that is created has very, very similar properties with the traditional sum-product ring, like the maximum is commutative, operations associative. It distributes, the addition distributes over the max, but the maximum, as a generalized addition, has one characteristic property that the ordinary addition does not have. It's idempotent. So 3 max 3 is 3, whereas in ordinary arithmetic, 3 plus 3 is 6, of course. And that's why the Russian group of mathematics have called this kind of algebra idempotent mathematics. Another, I would say the biggest difference between the traditional arithmetic ring and its algebra with the max-plus is the lack of inverse of the latter. So we can really solve easily equations like 3 max x equals 6. What is x? Sometimes we can find solutions, sometimes we cannot find solutions. But there is a way to bypass this weakness, let's say, of the max plus algebra. Here you see some numerical examples of how we multiply metrics and vectors in max plus algebra. I use this symbol. I'm trying to find a pointer on the slides. Okay. I don't seem to have control of it. This one in any case, it doesn't seem to want to be controlled. So I will just mention and kind of point your attention to several equations. So I use this symbol of which is kind of a box plus symbol to denote the max plus multiplication of a matrix times a vector, or the max plus multiplication of two matrices, capital A and capital B. The ij element of this multiplication will be obtained by taking, let's say, the ith row of matrix A and the jth column of matrix B, and instead of performing a linear inner product of these two, of this row and vector, we perform a max plus non-linear inner product. Instead of taking sum of products of the elements AI and B, IL and BLJ, we take the max of their sums. And you see an example here, a numerical example, where we multiply matrix A on the left with another matrix B on the right, and we produce a new matrix, let's say, whose element 1, 3 is obtained by taking the max plus inner product of the row that you see here of matrix A with a column matrix B, and instead of multiplying these two vectors in the traditional way, sum of product, we do a max plus. Now, in the finite dimensional case, the max plus matrix algebra consists of operations like the one I described, which is, I would say, the most general operation, the max plus product of two matrices, capital A, capital B. I will be using capital boldface letters for matrices, lowercase boldface letters for vectors. Now, for vectors, we can use the max between two vectors or the max between two matrices, and this max will be meant pointwise or minimum pointwise. Now, instead of multiplying a vector with a scalar as we do in linear algebra, in max plus algebra, we add a constant c to a vector x pointwise, or we add a constant c to a matrix, again pointwise. Now, what we do now with a mean plus algebra. For the mean plus algebra, I use the same box plus symbol, but with a prime. So when you see the prime, then we are doing mean plus algebra, mean plus multiplication of a matrix with another matrix, or a matrix with a vector. So this will be one of the notations. Max plus algebra have been used in discrete event dynamical systems, which are state space dynamical systems. You are probably all familiar with linear state space representations of a dynamical system. Well, we replace now the right-hand side. Instead of having linear products of a matrix A with a matrix B, we have max plus products between a matrix A and a matrix B. And the question is, what can we model with these max plus dynamical systems? In operations research and in scheduling and in automated manufacturing, we have the discrete event dynamical systems. Here is a very well-known and a useful application example. Suppose we have, let's say, a chain of conveyors in an automated manufacturing process, and we consider, let's say, discrete time state vectors where there are components xi of k denotes the time that the product k enters the ith conveyor. And the control input u is the time we put the product k in the first conveyor from the left, and then the constants T1, T2, T3, and so on are the times that a product has to wait inside the conveyor to be processed. Okay, and then we constrain the whole process by considering that only one product in a conveyor during each cycle. So then it's fairly easy to follow this example from a well-known publication in nonlinear control, that these three states, x1, x2, and x3, which again they represent the corresponding times that the kth product has entered the conveyor 1, 2, and 3, you see that they evolve like a nonlinear dynamical system. And this nonlinear dynamical system is precisely of the max plus type. The right-hand side can be expressed as the product of a constant matrix A, max plus, with the state vector at k1, at k minus 1, plus and another term, which is a constant matrix B, max plus with control input. Now, the right-hand side, I mentioned another term with a matrix B, but this other term is not summed with the first term. It's maxed. So this one, very broad application area of max plus systems in automated manufacturing, discrete event systems. Another application is dynamic programming. Suppose, let's say, we have taxi drivers driving in a network of cities and airport and trying to maximize their profit. The state, we have, let's say, 4 states, x1, x2, x3, x4, corresponding to city 1, airport, city 2, and city 3. And the discrete time, let's say, signal xi of k is the maximum profit that can be obtained by reaching at time k the state I. So the whole process begins, the taxi, let's say, begins from with 0 profit from state 1. So then the taxi driver wants to find what will be the next state, where the next city or airport where the taxi would like to go, so that at time k plus 1 maximizes the profit. And the result is, this is a dynamic programming, a classic dynamic programming problem, and this can be framed as a nonlinear dynamical system where the state at time k plus 1 is equal to a constant matrix A, max plus product with the state vector at the previous time. Again, this is a very broad area. Another very broad area of application of max plus algebra, actually min plus algebra, is speech recognition. Before deep learning was heavily applied to speech and language processing, the state of the art for speech recognition was a system called CALDI, where all these HMMs that were used for speech recognition were implemented on graphs. Graphs represented weighted finite state transducers, and the various optimizations needed for applying the HMM methodology. HMM means, for those who are familiar with it, hidden Markov models. So the methodology of HMMs was essentially being implemented using min plus arithmetic on these graphs represented weighted finite state transducers. Here, for example, you see an HMM transducer using min plus arithmetic, which converts an input speech signal into a sequence of context-dependent phone units. Another broad application area is computer vision. Well-known algorithms like distance computation can be formalized using min plus dynamical system. Here, for example, you see a shape, like this spiral shape, and the goal here is to obtain its distance function. Then the distance function can be obtained by iterating these min plus recursive difference equations in two ways. Let's say from top left to bottom right, and then take the result, the intermediate result, and work from bottom right to top left in reverse. And you see the result here in the bottom right of the distance function of let's say a robot vehicle trying to navigate itself within the corridor, and the navigation is done in following, let's say, the medial axis, which is it's the crest line of this distance function. So many applications in computer vision and robotics of finding this distance function recursively. And again, this recursion is essentially a min plus dynamical system. Now, how one can generalize these already existing applications and fairly well known, one way of generalize them is to replace in the max plus arithmetic, to replace the plus, the addition, with another operation, star operation, which distributes over max and over mean. I will not cover this generalization, but this generalization comes under the name of tropical operators, okay? And these tropical operators manipulate vectors in finite dimensions or signals in infinite dimensions. They manipulate them over spaces that are not the traditional linear spaces that all of us are familiar with. These spaces are non-linear spaces. We may call them tropical spaces. They are based on lattices. Okay, the simplest example is of a lattice is to have a set of vectors or signals and define point-wise max and point-wise min on them. Using these ideas, there are fairly many application areas. In computer vision, we have these moving local max-min filters. In neural nets, we have the so-called the max pooling layers in deep neural nets. Now, if in these max-min operations we also enrich them with the plus, and have max plus, so we have weights, then we end up with the so-called max plus convolutions or min plus convolutions. In the first case, the nonlinear spaces are flat. Their operations are only maximum and minimum, either on numbers, on vectors, on matrices, on signals. In the second case, the lattices are richer. They have max, they have mean, but the max and the mean is combined with weights, and these weights are additive. So these weighted lattices, we call them tropical spaces, and this will be the most general type of nonlinear space where these operations that I'm talking about during this tutorial take space. Now, from an area where these lattice operators have appeared for the last 30 years is mathematical morphology, well-known area in nonlinear image processing and computer vision. 4 types of operators that are very useful from this image analysis methodology are the operators that are denoted in this slide as delta, epsilon, alpha, and beta. The delta operator, which is called the dilation operator, is defined in the following way. If we have, let's say, a class or a collection of singulars or functions or vectors Fi, and we take the max of the point-wise max of them, and we apply to them this dilation operator, then this distributes over this max and gives us as output the max of the individual operator applied to each one of them. So in simpler words, these operators obey a max superposition. Operators that obey a minimum superposition are called erosion operators. These operators share a property called increasing, which means if we give them in the input 2 vectors fg, or 2 functions fg, where f is smaller than g everywhere, then the outputs of these operators obey this ordering. So this is called increasing property. If an operator is now increasing and anti-extensive, which means its output is less than or equal to the input, and idempotent, which means if we apply twice, it gives the same result as applied once, then we call these operators opening operators. We denote them usually by alpha. And for us, they represent geometrically a projection, but not a projection of the type that we all know from linear spaces, a projection on lattices. So I repeat again, these lattice projections are operators that are idempotent, which means if we apply them twice, you get the same result as apply them once. They're anti-extensive and they're increasing. A dual projection is the beta projection or closing operator, which is increasing idempotent but extensive, meaning the output is greater or equal to the input. Now, these 4 types of operators can be related with a very interesting double inequality, which is called Galois connection, or in mathematical morphology or in lattices, it's called also adjunction or residuation pair. This means that if we are given a dilation operator delta, there is a unique erosion operator epsilon, so that this pair is it's a pair of 2 operators where each one of them is adjoint to the other. And they are adjoint in the following sense, that if you find any vectors or any signals f and g such that delta of f is less than or equal to g, then this will happen if and only if f is less than or equal to epsilon of g. And if you find such a pair, then you can create projections very easily by taking, for example, the serial combination of an erosion and a dilation. Depending on which one is first and which one is second, you obtain an opening projection or a closing projection. So we'll be dealing with these 4 types of operators as a way to solve nonlinear equations for optimization. So again, I repeat, this concept of a tropical operator is a nonlinear, I would say, version of what we know as linear operators on linear spaces. What we call a linear operator in a linear space? An operator gamma, where if its input is a linear combination of vectors or signals, then the output is the same linear combination of the individual outputs. Well, a tropical operator of the max type, it's an operator delta, like a dilation, where if its input is a maximum of vector or signals added by constants, then the output will be the same max plus combination of the individual outputs. You see the analogy and how we go from summing vectors or signals, we take their max, and by multiplying them with constants, we add them with constants. From computer vision, I will show a few examples of operators in case some of you are not familiar with that. For example, a dilation of a shape X with a small disk dilates the shape, and it's the so-called Minkowski addition that I mentioned before, whereas eroding X by B shrinks the shape. The dilation of two shapes or of two signals is usually denoted in computer vision with this symbol of a circle with a plus, whereas the erosion is denoted with a circle with a minus. And if you cascade meaning a serial combination of the two operators, erosion and dilation, you obtain an opening, which is a smaller shape, smoother than the original. It's kind of like a smooth projection from the inside. Whereas if you take the dilation and then the erosion, it's kind of a smooth projection from the outside. Same ideas apply to functions, let's say images, where you see a gray image here in the top row, and next to it on the right, it's dilation by a small shape, and it's erosion. The dilation brightens the image, the erosion darkens the image in local neighborhoods. Then if we cascade the erosion and dilation, we obtain in the bottom the two nonlinear projections, which are nonlinear smoothers. The opening on the left, the closing on the right. These examples that I've shown from shapes and images, these pairs were designed so as to be adjunction pairs. That's why it was easy to combine the effect of a dilation and erosion serially and obtain a projection. Okay, so I would skip this example from mathematical physics because it takes some time now to analyze it. I will only mention its main idea that in computer vision, linear convolutions, which of course depend on sum of product type of operations, linear convolutions with Gaussians are solutions of the very well-known heat diffusion partial differential equation. If on this heat diffusion equation we do dequantization, then we end up with a nonlinear partial differential equation whose solutions are these tropical convolutions that I mentioned before, meaning the erosion or the dilations of functions by other functions. Okay, I emphasized the concept of adjunction, which again I repeat, it's a pair of a dilation and an erosion operator, and this pair every operator in this pair is unique to the other operator. We can use these pairs of operators to solve nonlinear equations in an optimum way. And this is one of the main applications of the optimization I mentioned in this tutorial. Consider the following problem, which is the analog of the central problem in linear algebra. In linear algebra, the main problem is to solve a system of linear equations, A times X equals B. Now, in max plus algebra, the corresponding problem is a matrix A, X plus product with an unknown vector X equals B. How do we solve this system of max plus equations? We can solve it, we can try to solve it exactly, or we can solve it approximately by minimizing a norm of the difference A max plus X minus B. The norm can be either L1 norm or L infinity norm or L2 norm and so on. Well, there's a famous theorem by Cunningham-Green in his book on minimax algebra, which gives us the following result, that if there's a solution of problem 1, of the exact problem, then there is there's an infinity of solutions, and the greatest of them is the mean plus product of the data vector B on the left with the matrix A, the adjoint of the matrix A. What is the adjoint in max plus algebra is taking the negative of the matrix A transpose. So this A star matrix is the matrix A transpose and negative. Okay, very simple. So then, if we take the mean plus product between the A star matrix and the data vector B, we obtain the greatest solution if it exists, but if it doesn't exist, if the system does not have an exact solution, we obtain the greatest subsolution, which means that this X hat is the greatest solution from below. And now, by using this concept of adjunctions, we can interpret the result using dilation and erosions. Dilation and erosions in finite dimensional spaces, which means if I multiply a matrix A in a max plus way with a vector X, essentially I'm doing a dilation of vectors. If I do a mean plus a product of a matrix with a vector, I'm doing an erosion. So by saying then that this X hat is the greatest subsolution, how come? So a very easy proof of that is by using this concept of adjunction that I mentioned before. Let's look at this. The product of A star mean plus with a vector B, it's an erosion. Now, I'm claiming that this is the greatest subsolution. Truly, if I multiply it on the left with a matrix A, then I have a dilation following the erosion. So this combination, erosion followed by dilation, it's an open, it's a projection. It's the best way of approximating the data vector B, but from below. Thus, therefore, this adjunction is a great way of geometrically understanding this optimal way of solving nonlinear equations that will appear very often in the applications that we'll consider in machine learning. And another nice thing about it is that the complexity of this solution is small. If the matrix A has dimensions m times n, then the complexity is actually m times n. Whereas in linear algebra, finding, let's say, the pseudo-inverse or solving a system of linear equations by minimizing, let's say, the L2 norm, the complexity is higher. So here, what we are saving here is we don't need an inverse. We don't need to find the inverse matrix in the system of max plus equations because this combination of erosion operator and a dilation operator gives us a pair of an adjunction, a Galois connection, and this Galois connection gives us a nonlinear projection from below the data. Okay, so we should remember this for the applications that will come right now. Well, we have now the break, but since I started late, if it's okay with you, I would like to take perhaps 10 minutes from the break and kind of cover some of the material before the break. So I will start out with the first application area of this tropical geometry and tropical algebra to neural nets. Neural nets that have piecewise linear activations. Well, this type of neural nets include well-known cases of neural nets, either shallow or deep, that have ReLU activations, as well as neural nets that have max-out neurons. For this type of neural nets, an interesting concept is the concept of a linear region, which is defined as the maximally connected region of input space on which the output of the neural network is linear. Okay, so please remember this concept, the concept of a linear region. Now, one could use, let's say, this concept, and we can claim that if we have a network with more linear regions, then the network will have a larger expressive power. But there are some obvious drawbacks of this measure, because the number of pieces alone is not informative. Here, I skipped, I forgot to mention actually this, this example, where you see such a network, first layer, second layer, third layer, and you see how the number of linear regions grows. So the drawback of using this measure for the expressive power of a neural network is that just the number of pieces alone is not informative necessarily, because you can think of many very small cells. It's unclear how small perturbations of the network parameters can affect it. It only concerns, of course, piecewise linear functions, activation functions, and the number of linear regions is expensive to compute. Again, I remind you some of the notation here that we are using for the underlying arithmetic of a tropical geometry. We're using the max plus ring, where the addition actually becomes maximum and the multiplication becomes addition. And then we max vectors and we form the max plus products of two matrices or two vectors in the following way. This box plus symbol, again, I remind you, denotes the max plus product of matrices or vectors. And this max plus product replaces the concept of a linear product of two vectors by replacing sum of products with max of plus. Okay. The first result for a single neuron tells us that the number of linear regions for a single max-out unit is equal to the number of vertices in the upper half of the Newton polytope. Remember in the introduction I mentioned that every max plus polynomial can be represented by the vertices of the upper half of its Newton polytope. Well, now we have this additional result that the number of linear regions for this single max-out neuron represented by the max plus polynomial is equal to the number of vertices. And of course, this result includes, as a special case, neural nets with ReLU activations. Let's look at a numerical example. Well, we have here a two-dimensional max plus polynomial. You see in the bottom, you see its Newton polytope. And then on top you see the upper half of its extended Newton polytope, and you see 6 vertices, in the upper hull, and these 6 vertices correspond precisely to the essential terms of this function, represented by the max plus polynomial. Now, what happens now if we have more than one outputs? Then suppose we have n inputs for a layer, and then we have n neurons. Then the number of linear regions is upper bounded now by the number of vertices in the upper convex hull. Remember this operation between neuron polytopes. It's very essential. That's why I'm going back to remind you this operation here. We have 2 polynomials, P1 and P2. We take their sum. Okay, on the left in blue you see the neuron polytopes of the 2 individual polynomials, P1 and P2. If I sum the 2 polynomials, what will be the neuron polytope of the sum? It will be the Minkowski sum of the 2 individual polytopes, which is shown here in red. So what happens then is when we have multiple neurons, then the polytope, the number of linear regions then is upper bounded by the Minkowski sum of the polytopes of the individual neurons. So we have n of P1, n of Pm, and so on, take the Minkowski sum, but this is only an upper bound. So this is another theoretical result, an upper bound. This upper bound can become tighter from work in tropical geometry applied to neural nets. It can become, let's say, tighter. This is a tighter bound, but again, it's an upper bound. And in practice now, how do we count the number of linear regions? It's not easy. Exact counting can be accomplished using insights from Newton polytopes, either by algorithms that enumerate vertices, but they can become impractical unless the problem is small, or by approaches like mixed integer programming, but again, they have several constraints. In our work, we have proposed some geometric algorithms that are randomized methods for counting and sampling essentially the extreme points in the upper hull of the polytope. You can find also works related to that, but not applied to neural nets, in computational geometry. There, the people in computational geometry care a lot about the Minkowski sum of convex polytopes. These are objects that interest them a lot. A recent paper by Guido Montufar and his group again provides sharper bounds for the number of regions. I will conclude this application of tropical geometry to neural nets by emphasizing these 3 theoretical results, which are very important. The first one tells us that every continuous piecewise linear function can be obtained as the difference of 2 max plus polynomials, or equivalently, the sum of a max plus polynomial and a dual mean plus polynomial. Another important result is that the essential terms of a tropical polynomial are in one-to-one correspondence with the vertices of the upper hull of the external neuron polytope. And essentially this gives us a geometric tool to analyze, understand, and design later neural nets by working with the geometry of their Newton polytopes. A third result concerns, again, neural nets with ReLU type of any depth, where the neurons there can be represented as a difference of 2 max polynomials, which is called a tropical rational function. Remember, in tropical arithmetic, the multiplication is replaced by addition. Therefore, the division can be thought of as being replaced by differences. I think I can stop here for a break and continue with the rest of the application areas. Consider a subclass of, it's actually a class of nonlinear networks where every neuron now has not just a nonlinear activation, but has a nonlinear structure. It's not just a sum of products followed by a ReLU or a max-out unit. It's structurally nonlinear, the network. And it's a max plus function. And before leaving for the break, I will just leave you with 3 questions. So far, the explosion in machine learning research uses this multiply accumulate paradigm everywhere for the individual neurons. 3 questions from our side. One of them is biology. Are the linear inner products and convolutions the only plausible models biologically for neurocomputation in terms of applications? How can we train neural networks if we include nonlinear nodes of the max plus type? And theoretically, can we use now results from nonlinear mathematics like max plus algebra and tropical geometry to analyze the behavior of these nonlinear nodes? So I will leave you with these questions and come back after the break.
We will come back in 15 minutes then.
Okay, returning back to where we stopped during the first part. So I left you with the following 3 questions. Are the operations involved in the perceptrons used as neurons for the modern neural nets, are these operations possible only to be as linear operations, or are they the only biologically plausible? Can we imagine neural networks with nonlinear nodes? Actually, there is biological evidence that nonlinear nodes in neural networks can model certain functions in biological neural networks. And how can we train them then? If we allow these nonlinear nodes to appear in the network, how can we train them? And a theoretical question, how can we use the result of some of the results in nonlinear mathematics? For example, some of the results that we have mentioned so far to analyze the behavior and the complexity of neural networks with such nodes. We will try to address some of these questions. Well, to remind you, this is the classical linear perceptron, a sum of products, inputs x1 through xn multiplied with weights w1 through wn, followed by some kind of nonlinear activation. Again, I remind you the concept concepts and symbolism of max plus algebra that we will be using. For example, we max vectors and we max matrices point-wise by using this lattice symbol of maximum, or we take the minimum point-wise of vectors and matrices by using again this lattice symbol of minimum. We add constants to vectors and matrices, and the most general symbol here is this box plus symbol between two matrices A and B, or a matrix and a vector, or two vectors, which means we combine their elements, row with column, combine them using the max plus arithmetic. And if we use this box plus prime symbol, then we mean min plus matrix products. Well, here comes the first definition of a nonlinear perceptron, the max plus perceptron. Tau of x, we have again a vector of weights W, we have a vector inputs x, and we combine the inputs and the weights in a nonlinear way by using max plus arithmetic. Or we have the tau prime perceptron, which is an erosion actually, and we combine the weights and the inputs using min plus arithmetic. There have been several researchers, notably Ritter and his collaborators, who argued about the biological plausibility of these nonlinear perceptrons, and they actually proved that they can become universal approximators within some assumptions. And they are related, of course, to a max-out unit. I mean, there are special cases of a max-out unit. Now, the first result here is the following. Suppose we have a binary classification problem. We are given patterns represented by some feature vectors x. K here is the index of the pattern, and these vectors are row vectors. And these vectors represent patterns from two classes, C1 and C0. C1, we may call them the positive examples. C0, we may call them the negative examples. And we consider the max plus perceptron with weights W. What is the definition of a feasible region? Feasible region for us is the set of weight vectors W, which completely separate the positive examples from the negative examples. It turns out that this can be formulated as a combination of two inequalities whose left-hand side is given by a max plus product of the sub-matrix of positive examples with the weight vector, and correspondingly the sub-matrix x negative of the negative examples with the weight vector. So if the weight vector W satisfies these two inequalities, then it belongs to the feasible region that separates completely the two pattern classes. And as you see, this set of vectors W is nothing else but a tropical polyhedron, because it falls in the intersection of two tropical half spaces, and we have named these intersections of tropical half spaces as tropical polyhedra. Now, to find a more applicable algorithm for this feasible region, in other words, to find an algorithm to test whether a given vector of weights or a given class of patterns is separable or not, we actually apply this theorem that I mentioned before, where this theorem, I remind you again, was about solving the system of max plus equations, solving them either exactly or approximately, and we saw that the optimum solution was a combination of an erosion followed by dilation, where the erosion was a matrix erosion, meaning the mean plus product of the adjoint matrix A star with the vector, data vector B, and followed by a max plus product on the left with the matrix A. In our case, the data vector B, if we look at the second inequality, the matrix X negative, max plus product with W, let's say equals to 0, then the 0 for us is the data vector. So by applying this theorem, we can prove right away the condition that you see here on the left. So if this condition is satisfied, then these patterns are completely separable. So it's a very easy condition to check. What happens now geometrically? How does this, let's say, separability condition, how can this be interpreted geometrically? You see on the right here the individual regions, assuming that our patterns are two-dimensional and that the red patterns are the positive ones, the blue ones are the negative ones. We see that the corresponding tropical half spaces are essentially unions of parallelograms, and where these parallelograms are, they have axes that are parallel to the two orthogonal axes of our coordinates. So the decision region then is at the intersection of such orthogonal parallelograms. And what happens now if we don't have this separability condition? So leaving from this slide, I would like you to remember that the decision regions for these nonlinear perceptrons, these max plus perceptrons, they consist of piecewise linear lines, or in 3D planes, piecewise linear surfaces, whose directions are parallel to the axis. Another generalization of this max plus perceptron is to take a linear combination of a max plus perceptron, the tau, and the min plus perceptron, tau prime. Again, the max plus perceptron for us is a dilation delta, and the min plus perceptron is essentially a matrix erosion, epsilon. And each one of them has weights. The delta perceptron has weight vector W, the erosion perceptron has weight vector M. And we form a linear convex combination. This is important, it's a convex combination. This convex linear combination of a dilation and an erosion perceptron is called the DEP, dilation erosion perceptron. So, there has been a lot of work during the last 30 years, I would say, to how to train these nonlinear perceptrons. I will focus more on recent approaches in the deep learning era, meaning approaches in the last 7 or 8 years. Starting with a new way of training these dilation perceptrons, or their combination of dilation plus an erosion perceptron. One new way is to use convex concave programming. When I say new way, I mean different from the traditional gradient descent and backpropagation. It turns out that we can train, let's say, a dilation perceptron, which means we can find optimal weights Wi by formulating an optimization problem that you see here that minimizes a function of J that has some slack variables xi, k, and these slack variables become positive if a misclassification occurs at the kth pattern. K here is the index of the pattern. We have introduced now some additional constants, Nk, which are proportional to 1 over the distance of the kth pattern from the class centroid, and we call that weighted convex concave programming. By the way, there are libraries in convex Python that one can use these libraries to very easily solve this weighted convex concave program. So by using this essentially new approach, one can design in an optimum way, optimum meaning it minimizes this functional that is reminiscent of the functional used in support vector machines. That's where we got the inspiration. And design an optimum dilation perceptron. Here you see a numerical example of designing an optimum dilation perceptron to classify two-dimensional patterns, either artificially generated, like the replay data set, or biomedical patterns from a breast cancer database. Both databases are really small databases, and what we found is that designing the dilation perceptron with this weighted convex concave programming gives more robust results, much fewer iterations than stochastic gradient descent, and actually better accuracy. And by using the weights in this minimization functional, instead of the plain support vector machine functional, one can actually regularize the whole procedure and make it more robust in terms of noise. So this is a positive experience, that there's a new way now of designing and training these nonlinear perceptrons, and the same idea can be applied to designing the dilation erosion perceptron, which is a linear convex combination of a delta and an epsilon perceptron. And it's very easy actually to see that this convex linear combination, it's a difference between two convex functions. Or a difference between a convex and a minus concave function. That's why it's called convex concave programming. Now, there is a major flaw, though, of these dilation erosion perceptrons. They suffer from the following disadvantage. They presuppose that there is a partial ordering both on the features and the classes. And suppose we have, let's say, two classes, the negative patterns N and the positive patterns P, and we want to separate them, like in this famous double moons example on the left. By simply inverting the classes N and P, the performance of the classifier might severely drop. One way to bypass this difficulty, this behavior, is to use the so-called reduced morphological operators based on a reduced ordering. Specifically, we pre-process the data by performing a reduced ordering row, and then we classify, not the raw data, but we will classify the reduced order data. Now, this reduced ordering can be obtained by via supervised training on a set of positive and negative examples. This kind of supervised training could be, let's say, a set of support vector machines with different kernels. So by doing that, one can avoid this major flaw of directly designing these nonlinear perceptrons and achieve good results on standard data sets. However, this convex concave training, while it's more robust and while it's theoretically interesting and algorithmically very interesting to pursue research-wise, so far there has not been a way to generalize it to large, very large data sets. It uses actually CPUs, not GPUs. So to deal and apply nonlinear networks like the ones I mentioned before to very large data sets, we had to go back to the good old stochastic gradient descent or ADAM and train large networks with such nonlinear nodes using gradient descent ideas. Here you see a dense morphological network, shallow but dense. Dense meaning that it has, let's say, 1 or 2 layers of, I would say, 400, in that order, 400 dilation neurons, or 200 dilation neurons and 200 erosion neurons. So we trained them using both stochastic gradient descent and ADAM by focusing on sparsity, meaning we applied a very simple baseline pruning methodology, the L1 methodology, which means that we keep only the weights after training with a very high L1 norm. Otherwise, if they have a low L1 norm, we prune them away. And we found the following interesting results, that of these dense morphological neural networks versus the traditional linear networks. But when I say linear, I mean multi-layer perceptrons with ReLU activations. The top part of this table of experimental results refers to the MNIST database. The second part, the below part, is the fashion NIST. Now, the various rows in each of these experimental results show different pruning ratios. 100% means we don't prune anything, and then 1% means that we keep only 1% of the weights, of the neurons, actually. It's a structured pruning. And we have several methods of doing that, either using ADAM or stochastic gradient descent on dilation neurons or erosion neurons, or combined dilation and erosion neurons, or linear neurons, feed-forward multi-layer perceptron with ReLU activations. Green shows the results where there is actually no loss of accuracy, even at a very high pruning ratio. As you see here, both with ADAM and stochastic gradient descent, we can maintain the same accuracy even with 1% only of the neurons, of the nonlinear neurons. So these nonlinear neurons, they exhibit a high potential for pruning. They can become very, very, very sparse and still maintain their accuracy. In contrast, the linear neurons, they do not behave like this. They quickly lose their accuracy. They lose their accuracy, as you see, from this shade of red in the fourth column. Now, comparing ADAM and stochastic gradient descent, where ADAM, of course, gives greater accuracy, but it has higher complexity, the stochastic gradient descent actually has an advantage. It gives even sparser results. An interesting visualization, this picture shows activations from one neuron, the same in all 4 cases. And the green-yellow colors show high values, the blue colors show low values. And as you see, the neuron in the feed-forward linear case with ReLU activations seems highly activated and difficult to prune, whereas in the left column here, either with the ADAM or better with stochastic gradient descent, you see that very, very few cases have high values, so it can be easily pruned. So the conclusion from these experiments is that these dense layers of such nonlinear neurons show a great advantage of being pruned. Now, there are problems though with training deep So far, I have talked only about either shallow or dense morphological networks. Now, what happens when we go to deep networks that contain these nonlinear neurons? It seems that there may be problems with training them, and we believe that this problem is due to their non-differentiability. Of course, PyTorch, for layers that have max pooling, which is a very, very, very simple version of a dilation perceptron, the max pooling, provides an answer. How? Well, it uses subdifferential. Otherwise, if one tries to use ordinary derivatives on these max functions, then you get these spikes due to Dirac functions, and one can do actually a smoothing of this Dirac, but this takes time and effort. Another thing we have found recently in a recent paper that you see here, training deep morphological neural nets as universal approximators, is that if you design a network whose layers consist only of max plus neurons or only of min plus neurons, then they are not universal approximators. Whereas there is a theoretical result that says you can represent a large class of functions, even linear functions, if you use just dilations or erosions. But if these dilations or erosions are of the type only of the max plus perceptrons, then they cannot become universal approximators. Whereas we have found out that if we consider a specific case of nonlinear neurons that have this exactly topology, and this topology we call it max plus min neurons, they're exactly a max plus dilation perceptron and an erosion perceptron with the same weights, the same weights W, and then sum both of them, and then multiply the sum with one simple linear scalar, A. So what follows then is just a very simple linear activation. Then we have found that these max plus min neurons are universal approximators. So this is an interesting theoretical result. And by using this new module, we can form multi-layer neural nets. And one can prove that these networks are universal approximator, provided that the network has sufficient depth. How much? Well, if the depth is in the order of the logarithm of the feature vector input dimension, then they become universal approximators. And we have actually trained them, these deep networks consisting of these new modules, the max plus min modules, and we have found that these networks are trainable and they achieve set accuracy, training set accuracy comparable to linear networks, and they outperform networks that consist only of max plus neurons or dilation erosion perceptrons. So in other words, if you make your neurons, your nonlinear neurons, to have this specific topology that I mentioned before, then you can achieve accuracy on very well-known data sets like the NIST and the fashion NIST, comparable to the linear networks, and you can enjoy, let's say, sparsity that these nonlinear networks provide. But their generalization capability seems to be somewhat worse than linear networks, but it's just the beginning. So these results are very new, and of course one has to examine them more carefully in many more cases before coming up with a more secure conclusion. We have also combined these morphological neurons with linear layers in a kind of hybrid network. Here you see a hybrid architecture where we have a backbone consisting of a traditional convolutional neural net followed by a hidden layer of these morphological neurons. So instead of, let's say, having the last linear layer at the end, at the top of a CNN, consisting of a simple max pooling, we have replaced the max pooling layer with full-blown morphological neurons. And we notice that the inclusion of this morphological layer leads to improved performance while achieving high sparsity. So it seems that these morphological layers have the ability of performing well while being sparse. So you can take this as a takeaway message that morphological layers of neurons, they can become sparse. They can achieve, let's say, accuracy comparable to linear layers, and the time to train them is actually smaller than training the linear layers. These are some of the conclusions that we have reached by either working only with morphological layers or in a hybrid way, linear combined with morphological layers. Okay. Now let me start now a new section where again we will be using the tropical geometry as a tool for intuition and as a tool for designing neural nets with much smaller number of neurons while retaining either the original performance or close to the original performance. One method is the so-called tropical division. A few reminders. The tropical polynomial, for us, it's a max plus polynomial. It's a maximum of several terms. Every term is an affine function. It has a slope vector, AI, and a constant bias vector, BI. If the Newton polytope, the extended Newton polytope is the convex hull of these vectors formed by the slope vector AI and the bias vector, whereas the simple Newton polytope is just the convex hull of the slope vectors. What happens now to the Newton polytopes when we sum or we max these tropical polynomials? We have already mentioned that. We will be using often this last result, which says the Newton polytope of the sum of two tropical polynomials is the Minkowski addition of the two individual Newton polytopes. A few visualizations of these ideas. Here we have two max plus polynomials, f and g. You see there are Newton polytopes here on the left. For example, the Newton polytope for the f polynomial is this linear segment. The Newton polytope for the g polynomial is this triangle. But you have to think of them in three-dimensional space because these are extended Newton polytopes. And to the right, you see the extended Newton polytope of the max of these two, of f and g, which forms something like a tetrahedron. And the Newton polytope of the sum of f and g is this triangle dilated by the linear segment. And it gives us this interesting geometrical shape to the right. So we'll be using this geometrical intuition a lot in the following examples. The general idea here is to use the geometry of neural nets in order to minimize them. In other words, to compress them into a smaller network that has similar performance with the original network. How do we do that? On the left here in blue, you see the original Newton polytope of the original network. On the right, you see the Newton polytope of the approximate network. And of course, it's Newton polytope, it's simpler, it's a simpler object. One method to achieve that is what we call tropical division. It's a new algebraic method that we have introduced a few years ago. And this method comes with a geometrical understanding using Newton polytopes. Well, you are familiar with the division, the ordinary division of two ordinary polynomials. We're given a polynomial P and a divisor polynomial D, the dividend and the divisor. We want to find two polynomials Q and R, the quotient and the remainder correspondingly, such that the dividend polynomial P is equal not to Q times D plus R, but the maximum of Q plus D, comma R. Again, in tropical arithmetic, the sum is replaced by max, and the multiplication is replaced by addition. That's why we have the addition of the quotient Q and the divisor D. However, the above division is not always possible, so we kind of relax the requirement, and instead of equality, we are content to have just inequality, that P of X will be greater or equal to this right-hand side. But we require that the Q and the R polynomials that we're after, they satisfy the above inequality maximally. And we have actually provided an algorithm for this approximate tropical division of max polynomials. I will explain this algorithm geometrically. In green here you see the upper hull of the extended Newton polytope of the polynomial P. In red you see the Newton polytope of the divisor polynomial. So what we do is like we shift horizontally and vertically the divisor polynomial all the way up until as high as possible, but we stay below the green upper hull. So if we do that, then we end up with a quotient. Here, for example, we see two examples. In both cases, the polynomial to divide is the same, both the left and the right example. It's a one-dimensional polynomial P of X, which is the maximum of four terms, 3x, 2x plus 1.5, x plus 1, and 0. Okay, so we have four terms, four vertices in the green upper hull. The divisor polynomial D of X is a maximum of two terms, x and 0. So its Newton polytope is this red shape. Now, the quotient polynomial, it's the maximum of 0, x plus 1, and 2x. Okay. In the first case, the remainder is, we have an exact division actually. In the second case, which is more interesting, you see in blue, you see the this blue triangular upper hull shape is the upper hull of the quotient polynomial, and in black, in dash black curve, you see the addition of Q and D. When I say the addition, the algebraic addition of the two polynomials Q plus D corresponds geometrically to the Minkowski addition of the Newton polytopes. So here in black, dash black, you see the upper hull of the addition of the two polynomials. And you see that this upper hull is smaller than the green upper hull, which corresponds to the original polynomial. So this here we have a case of not an exact division. So the general idea then is to minimize the network by matching the most important vertices of the Newton polytope of the max polynomials. Suppose we have just one output, then the neural network is essentially the difference of two max polynomials. For each of these two max polynomials of the network, we find a divisor by finding the most important vertices of the extended Newton polytope. How? By looking at the weights of the network and see which combination of neurons is activated by these weights. So this will give us, let's say, the most important vertices. And the most important vertices will give us the divisor. And then we perform the division and we simplify the neural network. You see here the polytope of the single output neuron in yellow being simplified and giving us kind of a simpler neuron as output in red. This whole process can be understood as a smoothing of the original polytope. For example, you see here on the left from the 8 vertices of the original yellow polytope, we kept only 4 blue vertices which comprise the vertices of the final red polytope. And there are several interesting properties of this tropical division method. The complexity is quadratic in the number n prime of the neurons kept, not the original neurons, the neurons kept in the smaller network. The algorithm is simple to apply. The question is how to extend that to multiple output neurons and perform not just binary classification, but multitask classification. One way we have applied this idea to multiple outputs is by using a one versus all framework, which essentially meant that we repeated the hidden layer several times, and every time we solved a binary classification problem, and we minimized each one of the networks. The result was promising on known databases like the MNIST dataset and the FASO MNIST dataset. This tropical division achieved good classification accuracies even at significantly large percent of compression, down to 5% or 10% of compressing. A better way of performing this tropical division appeared recently in this paper, and some of the improvements done for tropical division consist of the following two results. First, by using real coefficients, whereas before in the polynomials used we had integer coefficients. So now if we use real coefficients, then the pair of quotient and remainder polynomials can become unique. Further, there is an exact algorithm to find the quotient, which this exact algorithm goes as follows. Here on the left in blue you see the the graph of the original dividend polynomial, and in red, the divisor polynomial. Next to it, you see the graph of the difference of the two polynomials, p of x minus d of x. Now, the quotient polynomial can be computed as the best convex under approximation of this difference. So we take the difference, we consider its epigraph. The epigraph is essentially the graph of the function and all the points above this graph. And then we find the best convex under approximation. We find the convex hull of this epigraph. And then the lower envelope of this convex hull will give us the best quotient polynomial. So this is a better algorithm. And we have tried it again on known data sets, significantly outperforming baselines like L1 or other structured pruning methods like SNP, the single-shot network pruning. It has been applied to well-known data sets like the CFAR, either using the VGG topology or using the ResNet topology. And the pruning, the compression ratios are significant, as you see. However, in both cases, both the original tropical division as well as this improved tropical division methods, we have found out that if we insist on using the geometry actually of the whole network, then we may come up with even better ways of compressing the network. And this better way is I would say at this point, our best methodology, and it depends on the so-called Newton-Polytop approximation. I have been referring to neural network pruning or compressing neural networks or minimizing neural networks. What I mean, there are several ways of doing that, but what I mean here is a structured pruning. So we do not just eliminate individual weights, we eliminate whole neurons or whole channels. So this is called structure pruning. So whatever you hear in this tutorial about neural network compression will mean structured pruning. So let us see how we can achieve that using exploiting the tropical geometry of the neural network. Suppose we have one hidden layer and we focus on the ith hidden layer neuron. So this hidden layer neuron would be for us a max plus polynomial Fi, represented with its parameters that are the slope vector and bias vector Bi. Its Newton polytope, it's actually one line segment. So when we go and examine one of the output neurons, let's say the jth output neuron, the Vj, then this Vj function is just a linear combination of these max plus polynomials. And this linear combination can contain both positive coefficients C, Ji, or negative coefficients C, Ji. So we separate the positive coefficients from the negative coefficients. And if we take every group of same sign coefficients, let's say suppose take the positive ones, so this part of the output, we call it the polynomial Pj of x. Whereas the other part of the output, with a negative multiplicative coefficients, we call it the Qj. Now, if we just multiply a max plus polynomial with a constant coefficient, what we do is just we are scaling geometrically this linear segment. But if we add several of these max plus polynomials, then what is the resulting geometry? Remember, it's the Minkowski addition of these line segments. So these line segments become generators of polytopes, and these polytopes are formed by Minkowski addition of these line segments. We call this, each one of these line segments, we call it a generator, and the resulting polytopes are called zonotopes. So in computational geometry, when you form a polytope as the Minkowski addition of line segments, the resulting polytopes have a specific name. It's called zonotope. So we are dealing with zonotopes. So we have two zonotopes in the output, for every output. We have the zonotope resulting from the positive multiplicative coefficients that connect some of the hidden nodes to the specific output, and the zonotope corresponding to the negative multiplication coefficients. Okay, we denote the let's say, let me call it the positive zonotope with capital P, and the negative zonotope with a capital Q. Okay, and again, the parameters, the weight parameters of every hidden neuron, they correspond to the generator of the zonotopes, even when they are multiplied by these multiplicative coefficients to take us to the output. Now, we have now the extended Newton polytope and its vertices of its upper hull correspond to individual terms in these tropical polynomials. And what we want to do is to approximate one of these Newton polytopes, approximate it with another Newton polytope that is geometrically close to the original one. And if we, from the approximate polytope, if we go back to the polynomial domain, this will give us an approximate polynomial P tilde. So this is the idea. We will approximate the tropical polynomials representing the operation of every output neuron with other tropical polynomials, so that in the geometric domain of the Newton polytopes, the two corresponding Newton polytopes are close to each other. But how do we express being close to each other? With a distance function, which is called Hausdorff. It's denoted on these slides with the capital H. This Hausdorff distance has found applications in computer vision on comparing shapes based not so much on how different are the areas of these shapes when we try to match them together, but how many protrusions or intrusions has one shape different than the other. So this Hausdorff distance is very sensitive on thin protrusions or thin intrusions that one shape has different than the other. So the result, the theoretical result, the first theoretical result toward this direction is this one. That if we consider the original polytope capital P and the approximated polytope capital P tilde and their corresponding Newton tropical polynomials, then the error between the two tropical polynomials, the original and the approximate one, calculated using the L infinity norm, meaning the max absolute error on a unit ball, B, is bounded by the Hausdorff distance of the corresponding polytopes times the radius of this ball, B. Which implies that if we find a way to have the approximate polytope close to the original one, then the operation of the approximate neuron will be close to the original neuron. So our final theorem then combines these ideas, and if we consider two neural networks whose function is represented by tropical polynomials v and v tilde, with in the output we have m neurons, let's say, and each one of these m neurons has a positive and a negative extended Newton polytope, Pj and Qj, then the behavior of the original network versus the approximate network has an error. If you take their difference and compute the L1 norm of the difference over, let's say, a ball, B, then this difference is upper bounded by the sum of the Hausdorff distances between the positive polytopes and the negative polytopes for each output neuron added over all output neurons. Intuitively, if we have approximately equal polytopes, then we can safely conclude that we have approximately equivalent networks. Let us see a numeric result. Okay, suppose let's say we have only one output neuron, and here you see a layer of 1, 2, 3, 4, 7 hidden neurons. Then the output neuron will have two zonotopes, the positive in red color and the negative in green color. Then we have proposed a method to compress the networks as follows. We take the vectors consisting of the weight parameters of the hidden neurons, and we perform a k-means clustering of these vectors, and according to what k is, k, for example, is our desired number of neurons to keep. So let's say if k is equals to 4, equals 4, then this means we will keep only 4 out of the 7 original neurons in the hidden layer, and then the new weight vectors will be the representatives of these k clusters. So then you see that the new approximate network in the output will have two corresponding zonotopes, green and red, which lie inside the original zonotopes, and they are much simpler. And again, if we want to compare the behavior of the original network with a compressed network, we have to find the Hausdorff distance between the approximate zonotopes and the original zonotopes. Now, how do we extend this idea to multiple outputs? We have developed an algorithm which we called neural path k-means. Imagine a path going, let's say, from input to one of the outputs. Okay? This path will go through some hidden neuron, and then we'll go to an output neuron. Each hidden neuron will combine all inputs with some weight vectors, and then feed to one of the outputs. So we form extended vectors whose first part consists of the slope and bias vectors that connect the inputs to the hidden neurons, and then followed by the forward weights so that these are extended, let's say, vectors, and we perform a k-means clustering to these extended vectors, and then the final network is constructed by the clusters of this k-means procedure. So from input to output, you can think of it as being a neural path. So you have, let's say, neural paths that you cluster to have k only of them, and the resulting network will contain the parameters of only the remaining neural paths which are representative of these k clusters. Compare now to the previous geometric idea of compressing neural nets using tropical division. On both MNIST and fashion MNIST, definitely the neural path k-means perform much better. So we will stay with this method, and you can actually, this method appeared 2.5 years ago at ICLR, and it performed better than baselines like randomized compression or L1 structure pruning. It even performed better or comparable than ThinNet, which is state-of-the-art structure pruning method, but close to it. It did not surpass it. The most now recent version of compressing neural nets using these zonotope ideas, we call it tropical neural network compression, an acronym TROP NNC. It's a recent result. It has appeared as an archive report that you can find out more details. Let me just summarize for you the basic geometric intuition why this performs much better. And by much better, I mean it has outperformed state-of-the-art baselines as well as state-of-the-art on both CNNs and ResNets, both small data sets like MNIST and fashion MNIST, CFAR, as well as large data sets like ImageNet. Well, let me explain geometrically the main idea. The previous idea of reducing, compressing the neural network based on the zonotopes. Suppose, let's say, we have 3 generators, G1, G2, G3. Each generator corresponds to one hidden neuron. Remember, a hidden neuron has a slope vector as a tropical polynomial. I'm talking about neural networks with ReLU activations. It has a slope vector and a bias vector. Together, they give us a line segment as extended Newton polytope describing each one of them. So 3 hidden neurons, 3 generators, 3 line segments. The previous idea, which used k-means to cluster, the k-means takes, suppose let's say we want to compress the network, and from the 3 hidden neurons to keep only 2, of which 2 keep the first one, and the other, and the second and the third one, combine them together and come up with a new hidden neuron G2 tilde. Well, the k-means idea means that we will take the average of G2 and G3 and call that G2 approximate. Well, if you look at then the new zonotope, the new zonotope will be formed as the Minkowski sum of the G1 line segment that remain and the new G2 approximate. This will give us this purple, as a Minkowski addition will give us this purple shape, which is much smaller than the original octagon that you see here. Whereas, if instead of compressing the 2 hidden neurons and compressing them into one, by taking the average of the G2 and G3, if we take the sum, simple idea, but as you see, the approximation becomes much better geometrically. On the right here, you see that the new purple orthogonal parallelogram is a much better approximation of the original red shape. And therefore, the Hausdorff distance between the purple and the red zonotopes will be smaller, and therefore the approximation of the original network will be much better. So this is the main idea, and as you see, it was inspired and designed geometrically using the zonotopes. Here you see actually the algorithm for multi-output, because the idea that I explained before applies to single output. For multi-output, we have to think of the same idea simultaneously for all outputs. In other words, we want to compress the zonotopes of all outputs simultaneously. I will skip now the details. You can find them out in this reference. But there are two types of algorithms that can do that, either a heuristic, which is explained very, very similarly to the explanation I gave before, or an iterative method, which iterates on this geometric approximation until convergence. The iterative one will give better results, but higher complexity. Now let us look at the experimental results on deep neural networks, both with linear layers as well as convolution layers. In both cases, with green here, you see actually in the top row, the best method is this tropical neural network compression with improved version of compressing the network based on the zonotopes. It's in blue, and you see that it performs better than both the baselines, like random structured method, the L1, the red thin line, which is a state-of-the-art method, the previous neural path k-means. It performs better on linear networks as well as on convolution networks. It performs better, but in this case now you have to look at the green line, not the blue. The green line, because the green line, it's the iterative method, whereas before the blue line was so the blue line is the non-iterative, the green line is the iterative method. Let us go to more difficult data sets. CFAR, again, both on linear as well as convolutional neural networks. AlexNet topology, VGG topology, CFAR10, CFAR100. Again, the tropical neural network, in most cases, actually in the huge majority of cases and experiments, performs better in compressing the network than baselines and ThinNet. All this so far assumed uniform pruning, same ratio of compression in every layer. What happens now if we go to non-uniform pruning? There is a method, state-of-the-art method called CUP, and this method is a state-of-the-art. We have actually found out that by doing a hierarchical clustering instead of k-means on each layer, then we can extend the previous method to non-uniform pruning. The tropical neural network compression method has some similarities with the state-of-the-art CUP framework, but it has three notable differences. The first difference is that in one of the steps, instead of taking the representative of the cluster to be the max L1 norm feature map, it constructs the representative using tropical geometry. This is the most, I would say, notable difference. And when we compare it on ImageNet and the CFAR database, we see a difference. The tropical neural network compression method compared with the state-of-the-art method CUP, achieving similar compression, but it can actually provide higher accuracy, and sometimes this difference in accuracy is very big. Another thing we observe also, all this in VGG. If we go to ResNet, then the compressibility is not that great. We have not actually been able to explain this yet. One explanation is that the ResNet we tried doesn't have a very large depth. We tried ResNet 18, ResNet 50, and there the compressibility was not that great of this method. Now, I'd like now to switch to some applications of this tropical geometry and tropical algebra to other applications. But before doing that, I had mentioned before the capability of max plus algebra using adjunctions to find in an optimum way the solutions of max plus equations. We can also do that by enforcing sparsity in these solutions. And it's a hard problem, but it seems that it's doable. Let me remind you again of some of the main results between some of the main results in solving a system of max plus equations. We will be using these main results in the remaining of this tutorial. We have a system of max plus equations. Ax equals b, but Ax is not in the linear sense. It's in the max plus sense, which means we take the max plus product of a known matrix A with an unknown vector x to give us a data vector B. So A and B are given to us. We are after either an exact solution or an approximate solution. It's very rare, of course, as in linear algebra, especially for high-dimensional data sets, it's very rare that we will be able to find an exact solution. So let us focus now on the optimal approximate solutions. One type of approximate solution is what I have colored on this slide with red. It is obtained simply by forming the mean plus product of the data vector B with the adjoint matrix A, the matrix A star. Again, in max plus algebra, the adjoint matrix is the negative of the transpose of the original matrix. So, complexity-wise, this is very simple. It has complexity m times n only. So it is actually faster, a faster way of solving this system of linear equations than solving a system of linear equations with the same size. This solution x hat, it's optimum in the following sense. It is the greatest sub-solution. It's the greatest lower estimate of the data vector B. And we have proven that as we explained in the first part of this tutorial, by using the concept of adjunction. Anytime we perform a mean plus product of a vector with a matrix, this is essentially a vector erosion. Anytime we perform a max plus product of a vector with a matrix, this is a vector dilation. So in our case, what we have done is we performed a vector erosion B to obtain the solution x hat, and if we apply this solution to the original equation, meaning if we multiply it with the vector A, which means dilation, well, the serial combination of erosion and dilation gives us an opening, a projection from below, a projection which gives us the best approximation of the vector B from below. So if you take any error norm between B and the expression on the left, the x hat dilated by A, this error will have the smallest norm, both L1, L2, L infinity. However, it's an optimum solution, but it's a constrained solution. Why it's constrained? Because it gives us always something that is below our data. What happens if we don't want to have this constraint and we search for an unconstrained optimum solution? The answer is yes, we can find one, and I have colored that with green. How do we obtain this unconstrained unique solution? We take the previous greatest lower estimate, x hat, and we add to it a constant mi, and this constant is half of the L infinity error of the previous solution x hat. So we are given x hat, so we can very easily find the error from the data, take the max absolute value of the error, half it, and then add that to x hat. The result is the solution x tilde, and this solution x tilde is the solution that gives us the minimum max absolute error. So it's the best unique solution at the L infinity norm. So please remember these two theoretical results, the red and the green. The red gives us the greatest lower estimate. The green gives us the mean max absolute error estimate. Now, how can we go about achieving the same, let's say, solutions, but enforcing sparsity? As we have seen, if we enforce sparsity, one application is to end up with a minimized network, a network with lower complexity, especially nowadays where the networks have become so big. So obviously we would like to have a simpler network and a network with a smaller number of parameters, easier to train, but whose accuracy is close to the original one. So then, one way to achieve that is to sparsify the solution of these max plus equations. Let us formulate that in a theoretical way. We want to find a vector x in the as a greatest subsolution, but this vector x to be as sparse as possible. How to do that? Well, we can minimize the L0 norm. Okay, but it happens that this problem is NP-complete. It is equivalent to what is known in theoretical computer science as the minimum set cover problem. So in our work, we use the greedy algorithm, and we propose, let's say, using concept of submodularity, we proposed a greedy algorithm that can be extended to LP, not just L1, but other norms, to achieve these sparse solutions. The submodularity as a concept here maybe deserves a definition for those of you who are not familiar with that. A function of from sets to real numbers. Let's suppose we have a function f that takes a set as input and gives us a real number. Let's say some kind of a measurement of a set. Then the function is called submodular if the differential gain by adding an element to A decreases as the set increases. For example, if we have two sets, A and B is a larger set than A, then we add to A just 1 point, and then we form a difference between the value of the function f between the augmented A and the original A. And we do the same thing to the set B. And we find that the differential gain decreases as the set increases. Such functions are called submodular. So we have used these submodular functions to help us in deriving the greedy algorithm that I mentioned before and whose detail you can find in the reference paper. Talking about references, I will provide the slides of this tutorial, and at the end of the slides you can find a very large bibliography of all references that I have mentioned so far. One example of a submodular function is this following numerical example, where f is defined as the number of neighbors of a set of vertices in a graph. Well, this function, the set of neighbors of a set of vertices, is submodular. For example, suppose that the set A on the left is the black vertex, and the additional element that we add to it is the red vertex. And then on the right you see a larger set of vertices, the set B, which consists of the two black vertices. So if you apply this definition of the function f to be the number of the set of vertices, you find that the differential gain decreases as we increase the set. Anyway, after the first greedy algorithm, where we used the L1 norm, we were able to, in subsequent works, we were able to provide a similar greedy algorithm for other norms, where LP norms, where P is not just 1, but it can go up to L infinity. And we have been able to find, let's say, sparse solutions for the unconstrained optimal estimates of solving a system of max plus equations while imposing a sparsity condition. And this can be applied to network minimization as well as later on when we do regression, convex regression. So let me just provide this numerical example of compressing neural nets using these ideas. Suppose an experiment with just one hidden layer, and we want to find the pruning algorithm. The pruning algorithm here can find for us the sparsest approximation using LP norm where P is 20, let's say. In the experiments here, the original unpruned networks have hidden layers with 64 or 128 neurons. And in both cases, we want to compress them and have a hidden layer with only 10 neurons. Okay? Then look at the output. The output, the input vector is x, and the hidden layer forms a vector z, which is the matrix w times the vector x, and then the output, it's an output layer of max plus neurons, and the output vector y, it's the matrix A max plus the vector z. So the goal there is to compress the network, and this compression here was done with exactly zero loss of accuracy, while going from 64 128 neurons to only 10 neurons. And this was done by essentially trying to solve this system of max plus equations, finding a solution with a sparse solution. Let me now, before going to the last application area, which is regression, so far all the applications I have shown were from the application area of classification, pattern, recognizing patterns. The last application area will be regression. Before going to that, let me include a parenthesis here of some very recent ideas we're trying to develop on using this max plus algebra and tropical geometry for a new area called tropical approximation area. It's actually a mixed tropical dash linear approximation where we have a linear transformation of a vector x by a matrix AL, followed by a nonlinear transformation, which is implemented as a max plus product of the linearly transformed vector x by a matrix AT. Obviously, the indices L and T indicate that the two transformations being linear and tropical correspondingly. And we have a tropical polynomial, and we want to essentially approximate the output of some system with these mixed tropical linear maps. And there's a variety of interesting problems to solve here. We have identified at least 4 problems. One of them is max plus regression, for which I will talk later on. The problem of tropical inversion, where we are given the two matrices, we are given the target output, and we want to find the input by minimizing some kind of error function. A tropical regression, where by tropical regression I mean not just max plus regression, for which I will be talking later, but a combination of max plus regression after the patterns are linearly transformed. So we want to find not just the matrix AT for the max plus regression, but also the matrix AL for the linear part. And then tropical compression. To be consistent with the time constraint here, I will not cover all these areas. Let me just talk about the tropical inversion, which actually as a problem has several interesting special cases. One of them is fairly well known. It's Bellman's equation. Let us look at this. Suppose we have a Markov decision process. And we have two states, state 1 and state 2, And we have two possible actions, A, and we have possible rewards. The reward here is given as a function R, and this function R depends on the state where we are and the action we perform. And then we have the total discounted reward, which takes all these rewards and at various steps and multiplies them with powers of some constant gamma. So the Bellman's equation gives us the total expected reward Vs starting from a state S. And this Bellman's equation has this well-known form. The functions P with arguments subscripts S and S prime represent the probability, transition probabilities of moving from a state S to a state S prime under action A. Just fairly well-known ideas of behind Markov decision processes. So now, we can, suppose let's say we write out the Bellman equation for state 1 and for state 2. And we observe that if we subtract this value function from both sides, then we end up with these two equations in the bottom, which can take a form of kind of a hybrid linear max plus product. Specifically, we can have in this Markov decision process with two states, state 1, state 2, and two actions, and given the probability transition matrices P1 and P2, we can actually write, in terms of a tropical inversion problem, write this, this equation that involves both a linear product of the value vector V times the matrix AL that involves both the probabilities and the decay parameter gamma, as well as a max plus product of this result with a matrix AT, which involves rewards and some minus infinity constants. So, in conclusion, we can write this in dynamic programming, this in Markov decision process, we can write this Bellman equation by using this hybrid linear matrix product followed by a max plus matrix product, and we can embed that into solving this tropical inversion problem. If we want to solve this, and this tropical inversion problem has an interesting geometrical explanation. So let us state the tropical inversion problem as the problem of finding the unknown vector x such that the hybrid linear max plus, let me call that hybrid tropical product ALX followed by max plus product with the matrix AT is as close as possible to a target value y. Okay, so we can try to solve this tropical inversion problem by first solving the max plus inversion problem. Meaning, we can try to find first the vector V such that the matrix AT max plus V is as close as possible to a target Y. But we know how to do that. This is actually the solution to the system of max plus equations that I have mentioned already twice so far. And this optimum solution is this expression in blue. And this expression in blue is geometrically can be interpreted as projecting to the tropical cone and finding the vector v by using this projection, where we take the data vector, which is our target, take the data vector y, perform a vector erosion with the adjoint matrix A star, adding to it this constant in blue, which makes it unbiased optimum solution in terms of the L1 norm. So then finding this optimum vector v, it's essentially a lattice projection, as I have already explained. Why lattice projection? Because it's a combination of erosion and dilation. And then we have to solve the linear part, try to find the best matrix AL. Essentially, this brings us to the pseudo inverse, which is equivalent to doing a linear projection to a subspace. So then we have a tropical space where we project first, and then we have a linear space where we project second, and this combination can give us a very interesting geometric intuition of solving this tropical inversion problem. Well, there are several applications of this, but some of them are still under development. In this reference, in this publication, you find actually an application of tropical compression in recommender systems. I will skip the details of that because I want in these last 20 minutes to cover the tropical regression, which is a very interesting application area, and a very interesting application of the geometric and algebraic tools that we have discussed so far in this tutorial. Let me start with a well-known problem, how to fit a curve to data on the plane. So we're given a number of data with coordinates xi, yi, and we want to perform an optimal regression, regress y on the x. Well, if we use the mean square error, then of course the optimal solution is a straight line y equals ax plus b that minimizes the L2 norm of the error. And we can find precisely the parameters of this Euclidean optimal regression line, the slope A and the intercept B. What if our data are not clustered along a line? What if, as it happens in many practical cases, our data to regress, they form corners? Then the natural thing to do is not to fit to them a straight line or in high dimensional space to fit hyperplanes. A better idea is in one dimension to fit a piecewise optimal line, or in higher dimensions to fit piecewise linear planes. So toward this problem, again, I repeat the two optimal solutions of solving max plus equations. Again, we see here this algebraic problem of being very useful. I remind you the two solutions, the red and the green. The red is the greatest lower estimate. The green is the greatest unconstrained estimate of the data. by minimizing the maximum absolute error, so L infinity norm of the error. And again, the complexity of both of these solutions is linear in the size of the matrix A. So it's very fast. Let us try to fit a tropical line to our data. Suppose we have data xi and fi, and we want to regress and find, let's say, an approximation to this data with a tropical line y equals maximum of a plus x comma b. So, of course, there will be some error, and you can find two optimal solutions, the red and the green, by essentially solving a system of max-plus equations. So the two unknown constants in this tropical line, the constant A and the constant B, form a vector W, and we can form a data matrix capital X. The data vector F on the right is given to us. So from the given data, we can form both the matrix of the left-hand side as well as the vector on the right-hand side of our equations, and simply solve this system of max-plus equations with the optimal methods, the red and the green, that I have mentioned so far, and find, with linear complexity, find the best parameters W. And here is the visualization of the result. We are given data with noise, either Gaussian noise or uniform noise, of data around a line that bends on the plane. And if we try to regress this data with a Euclidean line, then of course the error is very large, whereas if we regress them using a tropical line, which means a max-plus polynomial, to find the max-plus polynomial of degree 1 here, you see that both the red does a better job than the blue, the Euclidean, and even better job does the unconstrained solution, the green one, in both types of noise. And we have actually performed extensive experiments with a variety of a lot of ablation studies with the size of the data, the types of noises, the amount of noises, and in all of these cases the results are the same. How about moving to polynomials of higher degree? We can actually try to fit not just polynomials of degree 1, we can try to fit max-plus polynomials of higher degree, here of degree k. Sometimes in max-plus polynomials, which again are a maximum of a number of affine terms, the number k here is called the rank of these max-plus polynomials. So if we know the rank, then try to find, let's say, the best max-plus polynomial of degree k that fits our data. It's identically the same problem of solving a system of max-plus equations, where the matrix of this system on the left is formed from the data given, and so does the vector on the right-hand side. And the optimal solution is obtained with a closed formula of linear complexity in cases where our data do not have just one corner point, but they have several, let's say, k corner points. How about moving to higher dimensions? Again, same ideas. Let's start from a plane, a tropical plane. Suppose, let's say, we are given data in 3D, data x, y, with values fi, and we want to approximate them with a tropical plane z instead of a linear plane, a linear surface z. Well, now this tropical plane will have three parameters. It will be the maximum of three terms, a plus x, b plus y, and a constant bias or intercept term. So these three parameters, a, b, and c, again, they can be found by solving a system of max plus equations. And again, this optimal solution, both the greatest lowers the greatest sub-solution as well as the green, the unbiased solution, which minimizes the L infinity norm, can be found with a closed formula, very, very simply. And you see the result here on data produced from points which were originally sitting on this piecewise linear polyhedra, and then perturbed by noise. And on the left you see the result with the red solution, and on the right the green solution. The difference in the two solutions is that the green solution is optimum and unbiased, but only with respect to the L infinity norm. The red solution is biased because it's always from below, but it's optimum with respect to any norm. Now, I have emphasized the fact that if we know the rank of the tropical polynomials that we want to use for solving, for approximating and regressing our data, then it's a closed formula solution. But what if we don't know the rank? Here, as a specific numerical example, we are given a number of triples in real three-dimensional tuples, xi, yi, fi, which come from a paraboloid perturbed by uniform noise. Actually, not uniform noise. The noise is Gaussian, but the points xi and yi were randomly sampled uniformly within a unit square. So we have a paraboloid. We sampled spatially a bunch of points. We took the value of the paraboloid. We perturbed this value with Gaussian noise. So we formed these 3D tuples. How can we approximate them with a tropical polynomial, a two-dimensional tropical polynomial? If we knew in advance that this came from a paraboloid, then of course we know the degree of the tropical function that we should use. We have a two-dimensional conic, and therefore the degree k should be 11. But if we don't know that, then there is a way. We have proposed an algorithm that has two parts. The first part employs the k-means algorithm on the data gradients to find the slope vectors ai, and then it uses the closed formula algorithm to find the optimal intercepts ci. And again, the complexity is linear, both in the number of data and in the number of dimensions. So it's a fairly fast algorithm. And you see how it performs on this noisy paraboloid sample data. We ablated the number k if it's unknown, and we found out that with a fairly small number of k, one can achieve a fairly good regression, close to the regression that one would get if one knew the exact degree of the surface. So in this case, for example, if we knew that, then the k would be 11. But even, let's say, with k equals 25 in the unknown case, we come very close to the k equals 11 known case. And the good thing about all this is that this algorithm has linear complexity and has closed formula, and it's connected with a result from optimal solutions of nonlinear equations. And since the solution here to this nonlinear regression problem, when I say nonlinear regression, I mean piecewise linear regression, but convex. All these max plus polynomials, of course, they give us convex functions. Since then, the optimal solution results from solving a system of max plus equations, we can try to go after sparse solutions of these equations. And then we can even further reduce the number of terms k. You see here, for example, the experiment on the same type of data. The red curve shows how the error, the norm of the error varies with the number of terms k, and the red curve, sorry, the black curve shows the result of smaller error with much fewer k. So sparsity again here can be very useful. And reaching our conclusions, I would like to mention that everything we have said in this tutorial about the nonlinear, the tropical algebra that underlies this new geometry, the tropical geometry, has been of the max plus type. So the max plus, let's say, polynomials are piecewise linear, and what happens if we generalize that to nonlinear algebras, the tropical algebras, the more general tropical algebras, where instead of max plus, we have max star, where star is another operation that distributes over max. Theoretically, it is possible. We can do it. Here you see some of examples. In red, you see what happens if I generalize to max product. In green, what happens when I generalize to max mean. Namely, I have replaced the plus operation in blue, of the blue case with the product operation in the red case, with a minimum operation in the green case, and below with a soft max operation, soft mean operation in this brownish case. So all this, it's actually a new area. One can experiment both theoretically or with data to see whether some different types of star operations can perform better than the max plus for some applications. This is still all very open. To my knowledge, has not been done, at least in the settings of machine learning problems that we have examined. In conclusion, the tropical geometry and its underlying max algebra, they provide principled and insightful tools to analyze neural nets with piecewise linear activations, as well as other machine learning systems. Special case of neural nets, where instead of having nonlinear activations, we replace them with max plus neurons. they can have similar performance with linear neurons, sometimes perhaps better, but let us stay with a similar performance, but superior compression ability and sometimes faster training. The tropical regression is very promising for fitting multidimensional data using piecewise linear functions, very low complexity algorithms, and optimal solutions. Tropical geometry can offer effective and insightful solutions for minimizing neural networks. For future work, it would be interesting to extend some of these results to non-convex settings. If you remember, all these max plus tropical polynomials correspond to convex functions. So the regression we talked about, it's a convex regression. What happens when we have non-convex regression? Let's say try to do regression with piecewise linear but not convex functions. Another open area for future work is to find training algorithms for these non-linear neural nets when we have the max plus neurons. I mentioned some simple cases of shallow neural networks where we tried successfully a new way of training them using convex-concave programming. But it has not been generalized yet to deep networks. Deep networks with nonlinear neurons may exhibit problems with non-differentiability of these nonlinear neurons. There are some ways to bypass it, but these ways are not theoretically